I showed this in the last video and we talked about the power supply for this project, but today we're going to dig in and see what this actually is. And what it is a clock generator for retrocomputing projects that I find myself working on quite a lot. And often I have a chip on a breadboard or a couple of chips, and I want to supply them with a very slow clock or a fast clock, or just experiment around. And I do have a function generator, but it's rather clumsy and it's a bit of a pain to set up. And then you've got the wires running down from the bench. And what I thought is, why not make a simple microcontroller based clock generator that ideally you could stick on the end of a breadboard like this one. This one is a bit yellowed, but you could stick it on here, and then you'd have your power supply shared, and then you'd have a single point where you could put a wire into whatever clock input you need. And then ideally you could also use it standalone without power here, and you could just supply power from the clock generator. It could have a little battery on it. And that's what we talked about in the last video, the power supply for this, which takes a single coin cell like this one here and basically steps it up to 5 volts, so we can produce a TTL level output. So let's talk a little bit about how this came to be and what sort of processes on there and what else. And for that, I'll just get the schematic. As you can see, this is relatively simple. We've got the coin cell here, go into the boost supply circuit that we talked about last time, and there's jumpers on here, or switches. At the moment it's jumpers, but in the final version it will be switches. So that you can basically turn off the boost converter and also isolate the boost section if you want to put power in through the breadboard pin and not output it. And then it has these two here which basically go down to the breadboard, a bit of support circuitry, two jumper links. And then we've got the actual business end here, which is, this is incorrect, this says 1890 S2313P, which is the predecessor to the AdTiny 2313, which I use in this project. But the library I have is rather old and the pinout's the same. So, and what this does is it basically has a crystal oscillator here and a couple of status LEDs and a switch input, and it basically uses the two PWM channels here to create clocks, different clocks of different speeds. And you could write some software for this to also output PWM or whatever you wanted. So it's quite a handy tool. And so you can reprogram it on the fly. There's a ISP socket on here. Also, a quick word about why I chose the ATtiny 2313. It's because I personally really like the chip. It's very cheap. It's one of the cheaper microcontrollers that Atmel or now Microchip offer. It has plenty of output pins, and it doesn't have all that much periphery on top of that, because I usually find that I'm severely underutilizing chips. I usually only need a couple output pins and a timer or two, or whatever on ADC. And usually chips have a lot more functionality that I'm just not using. So I like this for having a lot of output pins. So it's just a simple-ish chip. So that's why I like it. And now it's time that we look at the code that makes this project work. And then we can look at the actual project working. So most of the time on a project like this, you're going to spend on finding the bits that you've got to set to get the chip to do what you want. And that's what we're going to go over now, mostly. So we've got two PWM output channels on this, here and here. And one of them is 8-bit and one of them is a 60-bit PWM channel, or 16-bit timer, really. And we're first going to go over this and what these things do, and then we're going to go over this, and then we'll take a short look at the rest of the code, but it's really rather simple. So let's look at this first register here that we're doing stuff to, and we'll look at these 2 bits. Before that, we're obviously just setting the data direction register, but that should be fairly clear. So these 2 are down here, and what we're doing is we're setting them to toggle OC 0A on compare match. And we need that because we want to basically use this as a top value, and we'll look at this in a second. These WGM waveform generation mode, these are on the next page. And what we want is we want the fastest PWM that we can get, and we want to use our own top value. So we can set this to, for example, 1 and get very fast PWM, instead of a mode like this, where it would be set at a fixed value. And so what we're doing here is we're setting these to 1 and 1, and then trap here, this one, WGM2, is actually down in the next register here. So we also need to set that to 1, and then we get our fast PWM mode with this as a top value. So next thing, we're setting this value to 1, so we get very fast PWM, and we could change this later in the code, and we'll do it with this channel, but not this, because I'm not really using that at the moment. Although I have it output on the PCB, so this is just a fixed clock that you could use for whatever. Then the last thing is we need to set our prescaler, and we do this with these clock select bits here. And these are on this page. And what we're doing here is we're setting these to no prescaling. So we get the fastest PWM we can get, which with a 4 MHz clock is 1 MHz for this 8-bit PWM channel, which is plenty fast. This is definitely fast enough. So next we'll look at the 16-bit PWM thing here, which is basically the same in a little more complicated. We're setting our COM bits for the same thing. These are basically equivalent registers for this timer. We've got also the same setup here, except that we're setting this differently than up here. And we'll just look at this. Here our COM bits are 0 and 1, and we're setting basically the same mode as before, toggle OCA on compare match. This is the one we need. And then we're doing our clock select here, which I actually forgot about this. This is rather complicated, but it's also the waveform generation mode, like the last time we did this here. We've got these 2 set at 1 and this set at 0. So if we look at this, I need to find the right value here. So this is 0 is 1. Should be down here somewhere. This next one is also 1. 12 is 0. And 13 is 1. So it's PWM phase correct. This as the top value. Updated top, set flag on bottom. This is the one that makes it work. And then, as before, our clock prescaling, which is the maximum prescale that we can get. It's actually written in here wrong. This is not this, it's 1024. So this is basically what this is doing, is it's producing a very slow input clock. It's prescaled by value, and then we can make it even slower by setting this relatively high. Or we could change the prescaler in the program and make this low to get a fast clock. And basically that's exactly what we're doing in the rest of the code. Just defining us some input pins so we can take the switch input and output pins for the status lids. Then we're reading the switch, and then we just got some case break code here. And as you can see, we're setting for 1 megahertz, we set this low, and then we're turning off the prescaler here with these clock select lines, so, or bits. And as you can see, it just goes down like this. And actually these values are calibrated a little bit to give exactly the output that I want to have on my setup here. This is why this is such a weird value. I was hooking it up to the scope and trying to get it as close to 1 hertz as I could make it. And then we'll also switch off the LEDs at the end, because we're switching off a status LED here every time. And there's just a little bit of delay in here, so it actually has time to read the switch. Could also do that with an interrupt, but it's really not necessary here. So this is the code for this project. And now we'll look at the hardware prototype. And I've got a hardware prototype right here. And as you can see, it's got the battery on here. It's got a toggle switch here. This is the switch input that would turn it on. And then this is internal or external power supply. Here I have a jumper on there. But eventually I'd really like to use little switches like this. And put the whole thing in a 3D printed case to... so you can just switch them with your fingers or with a pen like this, poking through the case. And yeah, on the bottom, we've got the power supply circuit that we discussed last time, and we've got these 2 pins to poke into a breadboard, like this. So you can have this hanging off the end and supply your project with power and clock. And the improvements I want to make on this prototype to actually use it are as following. I'd really like to get the footprint further down, and I'm going to do this by, first of all, using a surface mount chip, which I didn't do in this prototype run because I'd really like to pull out the chip if the board doesn't work, so I don't lose a valuable chip, and it's just a little harder to do that with SMD. This crystal here, I'll use a small little SMD crystal like this, which has a much smaller footprint, so it can fit better into the case, because this is the highest component, except for this toggle switch, which I'm also going to replace with a smaller footprint one, and one that doesn't stick out as much. And yeah, as said, I'm going to change these 2 little switches. The output pins are on here, and I think we should actually look at how this works now. So I've got the thing hooked up to the scope, and this, the on-off switch, is just jump it over. And as you can see, if you toggle this switch, it'll just go to the next mode. And I'll insert pictures of the scope readout up here. Yeah, and that's the project. In the next video, we're going to look at the actual finished version and the 3D printed case, and then that project will be basically done. Also, another little update on the PCL 86 amplifier. As I said in the last video about this, I've sent the board to the board house, but due to the situation in China and worldwide, these are going to take a while to arrive. So sit tight. That project is not on hold. I'm still working on it, but I'm just not getting the PCBs out of China right now.